Professor Xiao-Ming from University of Science and Technology of China. Xiao-Ming is an associate professor at the School of Mathematical Sciences, University of Science and Technology of China. He received a bachelor degree in 2011 and a PhD degree in 2016 from University of Science and Technology of China. His research interests include geometric processing and computer-aided geometric design. The topic of the talk is piecewise developer approximation for triangular meshes. So now let's welcome Professor Xiao-Ming Fu. Okay, I will close sharing. Okay.
Okay, thanks for the introduction. I'm Xiao-Ming Fu from the University of Science and Technology of China. I'm glad to be here to present our recent work about the piecewise developable approximations. Let's first do some introduction. In manufacturing or in fabrication, the planar materials such as the iron sheets, wattage plants, and paper sheets are often easier to mass produce than curved materials. So, manufacturing no planar models by bending planar materials can save mass power and materials. So it often appears in many different designs, such as origami, shape healing, and clothing and architecture. So we can see here for this architecture, the surface of the architecture is a developable surface, and that can be fabricated by the planar material. In mathematics, the surface that can be bent from the planar material is called a developable surface. In mathematics, the developable surface is twice differentiable in motion with zero Gaussian curvature. So we can see that the developable surface is twice differentiable, and its Gaussian curvature is where zero. So this is a property. This property enables the development of the algorithm. However, most models are not globally developable, as the left models. So therefore, to fabricate with planar materials also is to compute a piecewise developable approximation to the input surface. And the requirement contains two main goals. The first one is the input and output. The approximation error between the input and output matches is small, and the piecewise developable has a small set of patches. However, this problem is challenging, and there are two common reasons. First, these requirements are mutually restrictively. As we know, a smaller approximation error often require fewer patches, so often lead to many patches. Second, the number of patches and is discrete variable, and the approximation often measured by the Hausdorff distance is a discontinuous function. So these discrete variables and discontinuous functions make it difficult to achieve the goal. Next, I will introduce our recent three works about on this problem. The first one is the developability-driven piecewise approximation for the triangle meshes. Let's first see some related work. The first one, we think to generate this developable approximation, the related work can be divided into categories generally. The first segment the segmentation-based method decouples meshes into patches and approximate each patch using a developable surface. However, since the segmentation is often directly performed on the input mesh, the approximation error is usually larger when after optimizing each patch to be discrete developable. Then the deformation-based method it first deforms the mesh to be developable. However, it does not have explicit patch layout. But we observe that although their results have no explicit patch layout, they have, as we can see, they have seam curves that can be used for segmentation. So according to this observation, we developed our algorithm contains 3 stages. The first stage is the deformation, which drive to the mesh to be nearly developable by an developability encouraged integer. Then as we can see in the deformed mesh, there are very silent features. Then these silent features can be used for the segmentation. So then we developed a cost-to-fine segmentation technique to partition the deformed mesh into a small set of nearly developable surface patches. Finally, this color means the Gaussian curvature. The refinement process is to optimize the deformed mesh to reduce the discrete Gaussian curvature to be approach 0 while keeping the patches smooth and the approximation errors small. Then I will introduce the 3 stages one by one. For the deformation process, this video shows the deformation process. Central to the deformation process is a new edge-oriented notion of discrete developability. So to make this deformation, we developed a new edge-oriented notion of discrete developability. Under the Gauss map, a developable surface degenerates to a set of curves. And this degeneracy condition can be moved from the continuous Gauss map to the discrete normals. So we use these properties to define our edge-oriented developability. In our definition, we instead of applying this degeneration condition to the triangle normal, we force the degeneracy condition on the edge normals to define the discrete developability. For each edge, the edge-oriented discrete developability requires the 5 edge normals. As we can see, the 5 edge normals to satisfy the left 4 determinant conditions. So if the left 4 determinant are zeros, then we call this edge is this edge is developable. So we use this deformation, or we use these conditions to drive the deformation process. Let's first to discuss this definition. In Zero, we find that our developability definition is weaker than the previous definition. So the deformed mesh driven by our developability energy is more flexible to the input shapes. We can see the second row. However, as although we use the edge normals, but although we use our edge normals, the mesh connectivity can still affect the deformation result, we can see the difference between these three ones. So to drive the deformation, we define energy function. The energy function contains the three terms. The first one is the age-oriented discrete developability. The second one is the approximation term to control the approximation error between the input and the output to be small. The third one is the distortion term, is to reduce the flipped and the degenerate triangles in the deformation process. However, as we know, the developability in our developability, we need to choose the four determined condition. So this determined condition is highly nonlinear and it is hard to minimize. To drive to perform the deformation, our key idea to overcome the challenge is need to introduce auxiliary variables to decouple the nonlinearity. Our auxiliary variables have 7 types. The first one is the rotation matrix R is used to encode the overall rotations of its normal and one ring. Then we use the face normal as an auxiliary variable to decouple the nonlinearity between the vertex position and the normals. Then we use the rotation U to represent the rotations of triangle normals with respect to the bisector as this one. Then we use the scaling S is as an auxiliary variable to measure the shift distortion. This is the PR is used to PR is used to denote the closed projection of a 3x3 matrix onto a rank 2 3x3 matrix space. PV is denote an auxiliary variable for the closed projection of a vertex position to the input mesh. With these auxiliary variables, we can define the integers. For the developability integer, we need to choose the determinant. This matrix is close to a rank 2 matrix. So if it is a rank 2 matrix, then its determinant will become 0. So our integer have these terms. For the approximation error, we need the VI to close its closed projection on the input surface. For the distortion integer, for the distortion term, we require the edges to be EIJ0 is the original edge vector. EI is the deformed edge vector. We need the EIJ is under rotation matrix, rotation and scaling. The scaling is very similar. Then to optimize this problem with 7 types of variables, we use the block nonlinear Gauss-Seidel method. Means we optimize each type of a variable block by blocker.
Because Professor Fu had some problem with his computer, so he need to use a new computer to restart the talk. So let's wait several minutes.
Okay. So I'm sorry. The computer. Yeah. Next, we will perform after the deformation. We will perform the segmentation. The segmentation contains 2 steps. Cost partition process that produce an over segmentation based on the normal difference between adjacent triangles. Then we will perform a patch merging stages that reduce the number of patches based on the discrete Gauss structure. So for the cost partition, we perform the segmentation one by one. For one patch, we define a developability metric for the segmentation algorithm. Then we find the unvisited patch with the maximal developability metric. Then if the metric is greater than a positive threshold, we use the elegant spectral mesh segmentation algorithm to segment this patch. Then we perform this process one by one. Then we can get a many over segmented result. Then we perform the patch merging. The patch merging also is one by one. Each time we merge one patch. We first find the unvisited patch with the minimal error and the set of its nearby patches. For each adjacent, each nearby patches, if its patch, if its boundary length is smaller than threshold, or there is a vertex with a high curvature on its boundary, we remove the adjacent patch from the catenator merging process. Then we choose the case that generates the most straight boundary after merging and merging these two patches. Then after the segmentation, we will use the previous refinement, a similar previous refinement method to reduce the Gauss curvature. But there are two differences. The first, our approximation term measures the distance from vertex to the deformed mesh instead of the distance from the vertex to the wrapped DOGs. Second, we do not cut the seam and duplicate the vertex on the seam. It avoids the gaps, so these gaps from between adjacent patches that appear in the previous result. After the refinement process, since this patch, each developable patch will be parameterized onto the plane for fabrication, but this parameterized patch may have self-intersection. So after the refinement process, we will cut the self-intersect patch and get the final piecewise developable meshes. Let's see some experiments. For the mesh with different tessellation, we can see that the hot-off distance between the input and our deformed mesh are small, and the generator patch are smooth and describable. The large noise caused the patch boundary to become more highly curved, but we find in practice that the noise does not lead to a large increase in the number of patches due to the cost-to-fine segmentation process. Besides, we test the deformation process on several developable or nearly developable models, and our algorithm generates faithful results. Here are 17 approximation results generated by our algorithm. Let's see some. We'll do some comparisons. To compare with the deformation-based method, we first use the method to deform the input mesh, and then apply our segmentation and refinement to generate the piecewise developable approximation. For the deformed mesh, they generate a larger approximation error, and their seam curves seem less silent. For piecewise developable approximation, they generate more patches, and their two-side hot-off distance are larger. To compare with the segmentation-based method, their result is poorer than ours. To verify the validity of our result, we fabricate some models. The fabrication process includes two steps. First, we print the flattened patches into the paper sheets and cut it. Second, we bend the cut patches and stick them up. We can see this video. This is the fabrication result of the bonding model. We rotated to let the more details. Here we show some more fabrication process and results. The airplane hand, the airplane. This is hand. This is a bird. Yeah, we have more results. We can see it. This is the kitten. This is a bird. This is a duck. This is a sheep. There are more fabrication results. This is a tools, fertility, fish. This is a kangaroo. This is a teddy bear. Yeah, this is a scanner. Yeah, maybe. Okay. So in this work, we present another method. Then the key idea is to combination the deformation based and the segmentation technique. Then the key contribution is an edge-oriented developability that is used to define developability in carried deformation energy. Then that is optimized by the block nonlinear Gauss-Seidel method. However, there are something can be improved. The first one is the edge-oriented definition of this developability is also depends on mesh connectivity. Second, our block nonlinear Gauss-Seidel method is slow. It used many times for optimization. The second, as we can see, the right fingers, the current result have many small patches and narrow regions in the patch, and the overall boundary length is long. So to solve this problem, narrow regions, small patches, narrow regions, small patches, and long boundaries, we developed a evolutionary piecewise developable approximation. As mentioned before, apart from the approximation area and the patch numbers, we also need this patch boundaries to be short. And penalty, we also need to don't want small patches and narrow regions. So, however, if we consider all these constraints and objectives, then these mutually restrictive requirements are also discrete and discontinuous. Then, as we know, it is very difficult to optimize them. As we know, the genetic algorithm is an optimization method similar to the process of population evolution in biology. First, it obtain an initial population of a series of individuals through a specific method. Then find a balance among various mutually restrictively measurements by define of fitness function. Through the evolution of the initial population and the genetic operations, the fitness function can be optimized. So we also use, our main idea is to use this genetic algorithm to optimize the mutually restrictive, discrete and discontinuous objects and constraints. So in our genetic algorithm, a chromosome is a partition. For a chromosome, our fitness function including those all quality metrics. They are, the first one is the approximation error. It used to encode the approximation error between the input and output shapes. The second is the number term. It includes the number of patches or total patches, the number of small patches, the number of narrow regions. So it includes three terms. Then for the boundary patches have two terms. First it includes the length of the patch boundaries and the smoothness of the patch boundary. The last one is the topology term. It used to ensure the correctness of the topology. In all these terms, the approximation term is hard to evaluate since it requires developable patches, which are difficult and time-consuming to obtain. So we cannot simply, it is non-trivial to evaluate this approximation term. To solve this challenge, we have a key observation: the approximation error and the mapping distortion. The approximation between the input and the output, and the input and its developable approximation are positive correlated with the mapping distortion between them. So this is a key observation. So we can compute the mapping distortion between the input and its piecewise, its developable approximation to estimate the approximation error. So based on this key observation, so we can transfer the approximation term to a distortion term, a mapping distortion term. The genetic algorithm, here we show a video to show the genetic algorithm. The genetic algorithm starts from an initial population consisting of many chromosomes. Then it performs the genetic operation, including selection, crossover, mutation to evolve the population to find a chromosome with a small fitness value until termination. Okay. So next we will introduce the genetic operations. So before for the first one is we need to introduce the initialization. To initialize a chromosome with small distortion, we use the cone parameterizations. So we first generate a set of cone singularity. Then we find a minimal spanning tree to connect the cone singularity. Then we use the VSA method to get an over segmentation result. So after the 3 steps, we get an initial partition. 2 initial different chromosomes to form a population. We adjust the cone singularity and the seed number in the VSA method. For the selection operation, we find that the elite selection makes Ellicent chromosome converging quickly. Then we get which we are trapped by a local minima. So we use the fitness values and the generation relation to output a new chromosome, and select only 1 chromosome among each parent and its children. So we will this children, this parent, we will they are a group to output 1 children. This one also. Then we introduce the crossover. Our crossover operation receives the 2 different chromosomes as input and output a new chromosome. It replaces a part of the patch boundaries of 1 chromosome with part of the patch boundaries of another one. Our mutation actions acts on a chromosome, and we develop 5 types of operations for different goals. And at each time we select 1 type of operations. They are merging patch operation, removing small patch operation, then the shorting boundary operation, removing narrow region operation. The final one is the smoothing trapezoid boundary operation. After run the genetic operation, we get a partition or we get a segmentation. With this segmentation, we deform the input mesh to be piecewise developable using the method of the first work. Here we show some experiments for the mesh with different tessellation. We can also get a reasonable result. In this work, we test our method on 240 models, including CAD models and organic models. Our algorithm successfully generates high quality results. Here are 12 examples. Also, we can run our algorithm on the developable or nearly developable models. We can see for this nearly developable models, we generate 3 patches with low approximation error. This is the comparison. Also, from the values, we can see that our results have smaller approximation errors and smaller numbers of patches and shorter boundary length than the competitor. Finally, to verify the validity of our result, we fabricate 6 models using paper. In conclusion, we present algorithm. This algorithm contains two key contributions. The first is the genetic algorithm. It is used to optimize the discrete and discontinuous objects. The second, we use the mapping distortion and the approximation. We use the mapping distortion to replace the approximation error to make the evaluating of the fitness function become easier. However, we do not including the human intuition, global smoothness, or global constraints into the genetic pipeline. If this requirement can be encoded with easily evaluated metrics, our genetic algorithms can be easily extended. Oh, okay. Let's go back to the limitation of the first. Another limitation of the first work. As we know, the age-oriented definition of discrete divisibility is the tessellation dependent. So we propose this work to resolve this problem. We use the new network. So as we know, we can see the middle column is the result of the first work. The deformation and the segmentation strategy means of the first work, the deform to segmentation strategy of the first work generates results that are with high quality in patch number and approximation errors, and than the genetic algorithm. However, the age-oriented discrete divisibility drives is tessellation dependent. So we can see the input tessellations are different than the deformed results are significantly different. So this is it is a limitation of the first work. So in this work, we want to resolve this problem to make the different tessellation with the different tessellation as input, we can get very similar deformed result. The key idea is to make the deformed tessellation to be tessellation dependent is to use the neural network for an implicit neural representation. So in this work, we use the implicit representation to be independent of tessellation. In detail, we use the SDF to represent the deformed mesh. The SDF is represented by a neural network. Then the deformation process is to update the parameterize of the neural network by optimizing a loss function. Then the SDF, the updated deformed SDF is extracted a triangle mesh that is further to cut. Then finally, we propose an algorithm to iteratively cut the patch to optimize the patch shapes for improving developability and the position and extra cut for overlap elimination. The final one, we can get the fabricated result. So in this new pipeline, we first learn this is SDF. Then we use a new network to deform the to perform deformation. Then we perform the initial cut. Then we use the iteratively cut to get the final result. Let's introduce each type in detail. So the first work is to the deformation. The deformation is driven by optimizing a loss function. So to generate a nearly developability implicit surface while approximation the input shape well, we define the loss function including 3 terms. To encourage the developability, this is the first one. Then to control the approximation error, the second one. Then finally, maintain the deformed implicit field as an SDF. This video shows the deformation process. We can see here some randomness. This randomness is caused by the neural network, the randomness in the solver to optimize the neural network. Then with the deformed mesh, we transfer the implicit field to a triangle mesh and find the feature point and for each high curvature region. Then we generate the initial cut by construct a minimal spanning tree that connects all the feature points. After obtaining the initial cut mesh, we propose an iteratively partition method to get the finally piecewise developable approximation. Each has 3 steps. The first is a discrete developability optimization step to reduce the Gauss curvature to approach 0. Then, this one, this is the remove overlaps. As we know, each patch will be parametered onto the plane. The parameterization shape may have overlaps. So this way propose a feature-guided overlap elimination stage to enforce manufacturability. Then we use a length-aware patch merging space to reduce the number of patches. Then these 3 steps are repeated until there is no self-section on the flattened patches. Then we output the result. Here we show some result of this. Here are the 14 examples. Here are the comparison. We can see that these results have few patches and smaller approximation error. This is the fabrication result of 6 models using paper to verify the validator of the result. Let's take a conclusion for this work. We propose a novel and automatic algorithm. The first contribution is use the implicit neural shape representation to make the deformation independent of tessellation. Then we propose a iteratively optimization process to enforce developability and manufacturability for each patch. However, it has some limitations. The first, the SDF training and deformation part takes most of the time. It often costs 7 to 8 hours. So it is worthwhile to speed up the training process and reduce the memory consuming. Although our cut is feature guided, but it is can be more intuitively for humans. So how to encode the human intuition into the piecewise developable approximation is feature work. So in this talk, I introduce the three works. The first one is the first one proposes age-oriented definition of developability to drive the segmentation, and combine the deformation and the segmentation to output piecewise developable approximation. The second one encode more using genetic algorithm to encode more constraints, more objects into the optimization to achieve a better result. The final work is using neural network implicit function to make the deformation to be independent of tessellation. Yeah, here are the three works, but the final feature direction, the one feature direction are still not resolved. Is not still resolved. It is the how to add the human intuition into the generation process. Means how can you make the result more likely? How can you get the results that are like to the human created? Thank you.
Okay, thank you very much. Thank you for the very nice talk. I have some questions to ask you. In the first and the second work, you prefer fewer patches, right? You minimize the number of the patches. But I think in some applications, it might be more desirable to find a reasonable layout of the patches. For example, when segmenting a human body model for garment design, right? Because a garment is to make a garment with stitch many pieces of clothes, right? And so when segmenting a human body for garment design, it might be more important for each patch to correspond to a specific piece of cloth.
Okay.
Right. So do you think it's possible to consider these constraints into your method?
Yes. Okay. I know this problem. This is also the last limitation I mentioned. For the garments or other something in some specific with some specific requirements.
Yeah.
We need to segment the models to meet the humans' intention. Yeah. So in our work, recently we do not encode this information in the optimization. This is the limitation. It is the key. It is the limitation. So in the genetic algorithm, if this constraint or this intention can be encoded by a function, then we can add it into the genetic algorithm. But some functions, some constraints or some intention are difficult to encode. So recently we may be using neural network to encode some high-level information, maybe a solution. Yeah, I think. if for example, for the governments, if you can know some cut or some high level information can be encoded into the deformation, encoded in the segmentation, then maybe we can get the desired, we can get the result meet the that meets the human's intention. Yeah.
Yes, I see. Okay, thank you.
Okay.
I have another question. We see there are many approaches to vector field computation, right? Like the one presented by
vector field.
Vector field computation method. I think. Do you think this method can be used for generating the developer approximation?
Vector field.
Yes, yeah, like the one
Oh,
presented by,
okay.
Yeah, in the first talk.
By the first talk, yeah. Last year we considered this last year, yeah, we try to encode this crossfield the information or something of the crossfield into the genetic algorithm, but we find that sometimes it will be conflicted with the developability requirement. Yeah, okay. So I think the crossfield or the vector field can, as the first talk is, it may be a global information. So I think maybe the neural network neural network can how can I say that? I know that one maybe last year or previous years, the vector field is used to segment the garments, maybe one paper maybe do that work. So I think it can be used, but how to encode this information and to make it compatible with the developability requirement, maybe need to more thinking or maybe to be more experiments. Yeah.
Okay, thank you. Okay, I think it's time to finish our webinar today. Let's thank the two speakers again. Thank you very much. Thank you all for enjoying today's webinar. Okay, thank you.
Bye.
Okay, bye-bye.